In today's lecture, we will be covering an introduction to transition metal chemistry. Transition metals are the 10 groups of elements situated between the s block and p block of the main group. They include groups 3 to 12 and are often referred to as the d block. The rest of the course will be mainly concerned with the d block elements in some way. The d block elements or transition metals are all metals that are good conductors, are malleable, ductile, have high melting points, and are shiny. Here are some examples of various transition metals, including copper, which is reddish, and gold, which is yellowish. Why do some metals have different colors? The color and shininess of metals has to do with their surface absorption and emission properties. Because the band gap in conductors is pretty much non-existent, absorption and re-emission of light is very fast. This is why metals are shiny. If all visible light is equally absorbed and re-emitted, then you get a silver color. For gold and copper, on the other hand, they absorb some wavelengths of light more efficiently, so they look yellow and reddish. This has to do with the density of unoccupied states at specific energy levels above the highest energy occupied valence bands that correspond to the wavelength of energy being absorbed. For copper and gold, there are more states that correspond to the energy of green and blue light, so more of those wavelengths is absorbed and they end up looking reddish and yellowish. So almost all of the d block elements display classic metallic properties, but there is one exception, mercury. Mercury is a liquid at room temperature and is a poor conductor. Why is only mercury a liquid? As a bit of a leading question, how do metals bond? Metallic bonding is often described as positively charged nuclei bound together by a sea of shared electrons. Because mercury atoms are bad at sharing their electrons, the bonds between atoms is quite weak, so it is a liquid rather than a solid. The reason mercury is poor at sharing electrons is due to relativistic effects. Mercury is one of the largest atoms and has a large number of protons in its nucleus. D orbital electrons are poor at shielding each other and penetrate somewhat close to the nucleus, so they experience a very large effective nuclear charge. Because of this, they have velocities approaching the speed of light and behave like massive particles with large amounts of inertia, which makes metallic bonding much more difficult because the valence electrons are more tightly bound to the individual mercury atoms. You might ask, then why isn't thallium a liquid? That's because you start filling p orbitals, which are higher in energy and less tightly bound to the nucleus, so they can more easily be shared and participate in metallic bonding. When looking at the transition metals, it's important to look at their valence orbitals. We will see that the chemistry of the transition metals is dictated by their d orbital electrons. In total, there are 5 degenerate d orbitals. As shown here, they have different phases and lobes. You will often see them superimposed on Cartesian coordinates, which helps in visualizing which orbitals are being referred to. Shown here is the dxy orbital, where the lobes are in the xy plane, but in between the x and y axes. The dxz orbital is the exact same as the dxy orbital, except that it is in the xz plane. Analogous to the previous two, the dyz orbital is in the yz plane. All 3 of these orbitals are orthogonal to each other, kind of like the p orbitals. The dx squared minus y squared orbital is similar in shape to the last 3, but it lies directly on the x and y axes in the xy plane. The final orbital is the dz squared orbital, which looks a little bit different from the rest of the d orbitals. It only has 2 lobes that lie directly on the z-axis, as well as a torus or donut in the xy plane as shown here. This torus is very important to remember because it plays an important part in determining the energy of the dz squared orbital in transition metal complexes. When looking at the electronic configurations of the transition metals, they can, for the most part, be represented by noble gas Ns2 n-1 d to the x, where x is a number between 1 and 10. There are a couple of exceptions, though. Can you think of which elements they might be and why? Just drawing out the orbitals here. Here is the 4s, and here are the 3d orbitals. So these will be filled, and when you go to scandium, you put in 1 electron here, titanium, 1 here, vanadium, 1 here, but when you get to chromium, according to the Aufbau principles, you would expect to fill this one here, and you'd have 3d4. But one of these electrons from the 4s actually jumps to the 3d, so that you end up with an electronic configuration that looks like this. And the reason for this is that there's extra stability when orbitals are half filled. So in this case, all the d orbitals and s orbitals are half filled, and chromium has an electronic configuration of argon 4s1 3d5. Then as you go across the period again, for manganese, you have 2s electrons. And then for iron, you put an electron here. For cobalt, nickel, and then for copper, you would expect, according to Aufbau, to have this electronic configuration. But once again, this electron will jump up here, and you have an electronic configuration where the d orbitals are completely filled and the s orbital is half filled. There's also extra stability when orbitals are completely filled. So in this case, you have completely filled d orbitals and a half-filled s orbital. So the half-filled s orbital has extra stability because it's half-filled, and the d orbitals have extra stability because they're fully filled. Lastly, when you get to zinc, you just fill the s orbital here, and you have a completely filled s orbital and completely filled d orbitals. So based on what we just discussed, both chromium and copper are outliers in that their electronic configurations are argon 4s1d5 for chromium and argon 4s1d10 for copper. This holds true for all elements in their respective groups. Once again, chromium and copper adopt these configurations because of the extra stability inherent to having orbitals half-filled or fully filled. One consequence of having so many valence electrons is that transition metals display a large variety of oxidation states, which we'll look at on the next slide. Starting with the first row, transition metals, this includes all the metals we looked at in the previous slide. So scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. The first row transition metals are often referred to as earth-abundant metals because they are the most common metals found in the Earth's crust. Looking at their common oxidation states, for scandium, only +3 is known. Can you explain why? It's because not too much charge builds up on the atom when it goes +3, and it can adopt a stable electronic configuration by losing 3 electrons. For titanium, +4 is the most common because it gives a noble gas electronic configuration, but +2 and +3 are also known. For vanadium, +3, +4, and +5 are the most common, but +1 and +2 are known. So pretty much from +1 to +5 are all possible. For chromium, +1 to +6 are all possible, with +2, +3, and +6 being the most common oxidation states. For manganese, we can see +2 and +7 are the most common, with +1, +3, and +6 also being possible. Plus 4 and plus 5, however, are not really seen. For iron, we can see a bit of a departure in oxidation states in that we cannot go to plus 8 and adopt a noble gas electronic configuration. This is because too much positive charge would build up on iron, which would be very unfavorable. Instead, plus 2 and plus 3 are the most common oxidation states, with plus 1, plus 4, and plus 6 also being possible. For cobalt, plus 1 to plus 4 are known, and plus 2 and plus 3 are the most common. For nickel, plus 1 to plus 4 are known, with plus 2 being the most common. For copper, plus 1 to plus 3 are known, with plus 1 and plus 2 being the most common. And lastly, for zinc, only plus 2 is really known. So what do the metals in the circled oxidation states have in common? The grouped oxidation states are all isoelectronic. That is, they have the same number of valence electrons. What oxidation state do you see the most? The most common oxidation state seen for all the transition metals is plus 2. Scandium is the only real exception. This is not just a coincidence either. There is a specific reason why plus 2 is seen for almost all of the transition metals. Can you guess why? It has to do with the orbital energies of the transition metals. The plus 2 oxidation state is prevalent because during ionization, transition metals lose the 4s electrons more easily. But aren't the 4s electrons lower in energy than the d electrons? For calcium, strontium, and isolated transition metal atoms/ions, this is true. The 4s is lower in energy than the 3d. The issue is, do we ever really deal with isolated atoms or ions in chemistry? Not really. When we do chemistry, there are always other things around, gases, solvents, etc. Atoms in isolation behave very differently from atoms under normal conditions, i.e., not in a vacuum with no other atoms around. As chemists, we actually want other atoms around. This is how we get chemical reactions to occur. So, for the transition metals, the s electrons are actually higher in energy, as shown by this graph. Can you think of why the 4s, for example, is higher in energy than the 3d orbitals? If a transition metal is surrounded by other molecules, atoms, etc., the electrons in those species will interact with the transition metal and its orbitals to some degree. So if you have a metal, say right here, and you have solvent molecules around, these solvent molecules will have some electrons that will interact with your transition metal. The electrons in the valence shell of your transition metal will be the most affected and will be repelled by the electrons in these other molecules, atoms. So in this case, the solvent molecules. This makes the orbital energies increase in general for the transition metal. The 4s in particular are more affected due to the shape of the orbital. Since the s orbitals are spherical in shape, they interact more with the surrounding species and go up in energy the most. You can see at all points the s electrons will interact with the solvent molecules. The d orbitals, on the other hand, only point in certain directions. So if you have solvent molecules here, like we did before, they will interact less with the electrons in the d orbitals. Because the electrons in the surrounding atoms, molecules, the solvent in this case, interact less with the d orbitals than they do with the s orbital, the energy of the s orbital increases more than the d orbitals. So based on what we just discussed, can you hypothesize what the ground state electronic configurations of the first row transition metals will be in the +2 oxidation state? Because the s electrons are higher in energy, They are preferentially ionized, and as such, the 2+ cations have only d valence electrons. This also explains why chromium and copper can adopt the +1 oxidation state. They readily lose their single s electron. For all other transition metals in the +1 oxidation state, other than in groups 6 and 11, one s electron will be lost, and the other actually moves to occupy a lower energy d orbital. So all transition metal cations have d outer shells. Shown here are some reduction potentials of the first row transition metals. In general, they are fairly reducing, and most lose 2 electrons quite readily. This also shows that for many transition metals, the +2 oxidation state is stable because the 2s electrons are higher in energy than the d electrons and are removed first preferentially. Now that we've covered the reduction potentials of the first row transition metals, I'm going to show you a real-world application that makes use of reduction potentials, which really shows why understanding these concepts is really important. The example I will discuss has to do with the process of galvanization, where you cover steel with a layer of zinc. One problem with steel is that when it rains, it is prone to rusting. What happens is that a small electrochemical cell forms when a water droplet sits on a piece of steel. A high energy site inside the water droplet, shown right here, so that's a scratch, a dent, or some other imperfection, it forms an anode. There, iron atoms in steel are oxidized to iron 2+ cations, which dissolve into the water. The electrons from the iron oxidation travel through the steel to the interface where water, air, and steel meet. So that would be right here. There, a cathode forms and oxygen is reduced to water. The protons necessary to perform this reduction come from the water droplet itself. That may seem a bit strange, but it is important to note that all raindrops are partially acidic, around pH 5 or 5.5 or so, due to the partial pressure of CO2 in the atmosphere. Moreover, rust formation is further exacerbated and accelerated by acid rain, which is caused by pollution. So when we look at the reduction potentials for this reaction, we can see that oxygen has a fairly positive reduction potential, 1.23 volts. Iron, on the other hand, has a fairly low reduction potential, minus 0.44 volts. Therefore, the overall cell potential is positive, and this reaction is thermodynamically favorable. Note that this reaction is not actually balanced and would be really good practice for balancing redox reactions. Another feature of rust formation is this second reaction shown here. The iron cations that dissolve in solution further react with oxygen in a second redox reaction. This reaction is also not balanced and is actually fairly tricky to do properly, so it would also be good practice for you to try. Anyways, the second reaction is what forms the reddish iron oxides that we associate with rust. What is critical about this process is that it doesn't allow a passivating layer to form over the exposed steel. The cations diffuse away from the anode and the iron oxides deposit elsewhere on the metal, as shown right here. Moreover, the formation of iron oxides actually generates protons, which further accelerates the initial oxidation of iron in steel to iron 2+. So when we look at the process of galvanization, it protects the steel in two distinct ways. First, when you coat the steel with zinc, the top layer of zinc oxidizes, but unlike iron, it forms a passivating zinc oxide layer. This forms a physical barrier which protects the steel underneath from water and oxygen. So why not just use paint? It can also form a physical barrier against water and oxygen to protect the steel below. This strategy is still widely used, mainly because it is a lot more cost effective, but a problem arises when the paint chips or gets scratched. The steel underneath gets exposed and starts to rust. The benefit of galvanization is that even if the zinc and zinc oxide layers get scratched, the zinc metal still protects the exposed steel. It does so by acting as a sacrificial anode. What this means is that when a water droplet forms around a scratch in the zinc layer, when the electrochemical cell forms, the zinc metal acts as the reductant rather than iron, as shown here. Looking at the reduction potentials, this should make more sense. The oxygen half reaction stays the exact same with a 1.23 volt reduction potential. But looking at zinc, we can see that it is even more reducing than iron. So when we look at the overall redox reaction, the cell potential is more positive for zinc as the reductant than was seen for iron as the reductant. This means the zinc will preferentially be oxidized, as this reaction is thermodynamically more favorable than oxidizing iron. It's only when all of the zinc gets oxidized that the steel will begin to rust. Sacrificial anodes are also used for underground pipes, although they aren't always coatings. Oftentimes instead, a large block of a more reducing metal than iron, such as zinc or magnesium, is connected to the pipe with a wire. So these concepts of reduction potentials have really important real-world applications. Now looking at some of the heavier transition metals in the D block, including yttrium, zirconium, niobium, molybdenum, etc. in the second row, and lanthanum, hafnium, tantalum, tungsten, etc. in the third row. These are some of the rarest metals in the Earth's crust. We're going to briefly take a look at their oxidation states. So for yttrium and lanthanum, they only adopt the +3 oxidation state, very similar to scandium, and for the same reasons. Zirconium and hafnium generally form the +2 to +4 oxidation states, with +4 being the most common. Niobium and tantalum can adopt +2 to +6, with +5 being the most common. Molybdenum and tungsten can adopt oxidation states between +2 and +6, with +6 being the most common for molybdenum, and +4 to +6 being the most common for tungsten. Technetium and rhenium can adopt oxidation states from +1 to +7, with +4, +5, and +7 being the most common for technetium, and +3 to +7 for rhenium. Ruthenium and osmium can adopt oxidation states anywhere from +2 to +8, with +2 and +3 being the most common for ruthenium, and +4 for osmium. For rhodium and iridium, +1 to +6 can be adopted, with +1 and +3 being the most common for rhodium, and +1, +3, and +4 being the most common for iridium. For palladium, +2 or +4 are known, with +2 being the most common, but for platinum, +2, +4, and +6 are possible, with +2 and +4 being the most common. For silver, +2 or +3 are known, and +1 is by far the most common oxidation state. For gold, on the other hand, +1 to +3 are known, and +5, with +1 and +3 being the most common. For cadmium, only +2 is known, whereas for mercury, both the +1 and +2 oxidation states are common. This concludes today's lecture. If anything was unclear, please feel free to ask questions during office hours, or try rereading the textbook to clarify concepts. And as always, there are some useful websites and resources in the links below to help with understanding some of the concepts that were presented today.